Good day. In this lesson, we will investigate constant acceleration and how we can use graphs of motion to understand this concept better. Now let's join Aaron in the lab as he investigates what happens when a trolley travels down a slope. Aaron has attached a syringe filled with ink to the front of the trolley. He allows ink drops to fall on the track at regular time intervals. If the trolley goes faster, the ink spots on the track are further apart. He will measure the distance between the spots to calculate the velocity of the trolley. Aaron wants to measure the change in position more frequently, so he has adjusted the dropper to drop the ink more often. Now, let us see what Aaron finds when the slope is large enough to have a constant acceleration.
The trolley runs down the hill, leaving a more frequent trail of ink spots behind it. The gap between each pair of ink spots represents the displacement of the trolley in half a second. Now notice that the displacement between the spots increases each time interval. Once again, we can build up a table of results of time, position and displacement. Now let's fill up our table.
We can see from Aaron's experiment that the displacement at each time interval increased. Now let's join Nelly so that we can analyze the results from a table.
Here is the completed table of results for the trolley going downhill. In the first half second, the trolley changed position by 0.05 meters. In the next time interval, the trolley was displaced by 0.1 meters. What is happening to the displacement of the trolley for each of the time intervals? Clearly, the change in position is increasing.
Now that we have a table of displacement versus time, Nelly shows us how to use it to draw a displacement versus time graph.
On this graph, time is the independent variable, so we place it on the horizontal axis, and the position, the dependent variable, is placed on the vertical axis. I'm plotting the data from the table onto the graph. Notice that these points do not lie in a straight line, so we can't use a ruler. I will draw a line through these points freehand. Look. This line swoops upwards with an ever-increasing slope. The gradient is small at the start but increases with time.
Note that this displacement versus time graph is not a straight line. Since it is not a straight line, the velocity cannot be constant. So let's see how Nelly uses the table to calculate the velocities of the trolley.
Can you calculate the velocity for each of the 5 half-second time intervals? Take a look at my results. For the first 0.5 seconds, the velocity is 0.1 meters per second. In the next time interval, the trolley's displacement increases, and so the velocity increases too. Here it is 0.2 meters. Can you see that the velocity is increasing for each of the time intervals? At 0 seconds, the velocity of the trolley was 0. But it increased to 0.5 meters per second during the 5th time interval. Notice also that this increase in velocity follows a pattern. The velocity increases from 0 to 0.1 in the first time interval, and then from 0.1 to 0.2 in the second time interval. In each of the time intervals, the change in velocity is 0.1 meters per second. We call rate of change in velocity acceleration. So this trolley must be accelerating uniformly in the direction of motion.
So, Nelly has shown us that this trolley is definitely not traveling at a constant velocity. In fact, the velocity increases uniformly. We call this constant acceleration. Now let's rejoin Nelly and see how this impacts on our graphs.
Remember when we analyzed the data in the table, we found that the velocity of the trolley was increasing. Does the position time graph confirm this conclusion? Remember, when Dineo walked slowly, the gradient of a position time graph was not as steep as when she walked quickly. So, we know that the gradient of a position time graph increases as velocity increases. On this position time graph, the gradient is increasing in steepness. So, the velocity of the trolley must be increasing as it runs down the track. The graph confirms one of our original conclusions. We also use the data about the velocity in each of the time intervals to show that the velocity was increasing in a uniform way. Do you think a graph can help us to find out how the velocity changed? Well, the position time graph is not very helpful here. We need to plot a velocity time graph if we want to find out how the velocity changed with time. Why don't you try drawing a sketch graph using the values of velocity from the table of data? Have a look at the graph I have drawn and compare it to yours. In this graph, time is placed on the horizontal axis and velocity on the vertical axis. Notice at 0 seconds, the velocity is 0. At half a second, the velocity is 0.1 meters per second. At 1 second, the velocity is 0.2, and so on. Let's look at the shape of this graph. Can you see it is a straight line graph with a constant gradient? This constant gradient tells us that the change in velocity per unit time is a constant, so the increase in velocity is uniform. Remember, the rate of change of velocity is acceleration, so the trolley was accelerating uniformly.
Now we know that the velocity time graph for constant acceleration is a straight line. Remember previously, for constant velocity, we use the gradient of the displacement time graph to calculate the velocity. But here, the velocity increases, so the displacement time graph is not a straight line. The displacement versus time graph for constant acceleration is a curve. If we join any 2 points on this curve, we can find the slope of the straight line. We use this line to calculate the average velocity between the 2 points. In this case, from 0.5 seconds to 2.5 seconds. So when we connect 2 points on a curved displacement time graph with a straight line, we use the straight line to calculate the average velocity. But we know that instantaneous velocity, the velocity at a specific point in time, can be calculated by finding the change in displacement over a very short period of time. As we move the points closer and closer to each other, we make the time interval between the points smaller. The line becomes the tangent to the graph at a specific time. This velocity, which is given by the gradient of the tangent, is called the instantaneous velocity. Let's use the gradient of this tangent to work out the approximate velocity at 1.5 seconds. We mark off 2 points on the tangent. We read off the x and y values of each of these points. The point A has an x value of 1 and a y value of 0.3. And point B has an x value of 2 and a y value of 0.6. Now we use the equation for the gradient of a straight line. The gradient of a straight line is calculated as the change in the y values divided by the change in x values. The gradient equals 0.6 minus 0.3 divided by 2 minus 1, which tells us that the gradient of the tangent to the graph at 1.5 seconds is approximately 0.3. Therefore, the instantaneous velocity at 1.5 seconds is approximately 0.3 meters per second. Let us now go back to the velocity versus time graph and discuss what information we can gather from this graph. We know from our definition that the acceleration is the change in velocity over change in time. We can represent this mathematically as acceleration equals delta v divided by delta t. Now, let's see how that would apply to the graph. If we apply this equation to the graph, we see that the change in velocity is actually the same as the change in the y value, and the change in time is the same as the change in x. Therefore, we can calculate the acceleration from the velocity versus time graph using the gradient. Let's do this now. The total change in velocity is 0,5 meters per second, and the total change in time is 2,5 seconds. So, acceleration equals 0,5 divided by 2,5, which equals a constant acceleration of 0,2 meters per second squared. Let's now use this information to draw an acceleration versus time graph. Since the acceleration is constant at 0,2 meters per second, we get a horizontal line through 0,2 on the y-axis. Next, we know that area under a velocity time graph gives us displacement. Let us confirm that by the calculation of displacement after 2 seconds using the velocity versus time graph. When we look at this, we can see that at 2 seconds, the velocity of the trolley is 0,4 meters per second. Using our knowledge that the area under a velocity versus time graph gives us the displacement, we can work out the trolley's displacement at 2 seconds. The shape of the area under the graph is a triangle. The equation for the area of a triangle is equal to half base times the height. So the area equals a half multiplied by 2 multiplied by 0,4, which gives us a displacement of 0,4 meters. Now, let us look at what information we can gather from our acceleration versus time graph. Acceleration equals the change in velocity over the change in time. We can rearrange this equation to make the velocity the subject of the formula. So the change in velocity equals acceleration multiplied by the change in time. Now let's see how we would apply this to the acceleration versus time graph. If we apply this equation to this graph, we multiply the time, let us say 1 second. By the constant acceleration of 0,2, we get the value of velocity, which is 0,2 meters per second. But what do you notice about the shape of this section of the graph? That's right, we have effectively calculated the area under the graph. When we multiply acceleration by time, we actually multiply the length of the rectangle by the breadth. Therefore, the area under an acceleration time graph gives us velocity. So in this lesson, we learned about constant acceleration, how the data can be represented graphically, and how these graphs can be used to do various calculations. To summarize, look at these 3 graphs that represent constant acceleration. The displacement time graph is curved, and the gradient of the tangent to the graph at a specific point gives us the instantaneous velocity at that point in time. The velocity time graph for constant acceleration is a straight line graph. We use the area under the graph to calculate the displacement at a specific point in time, and the gradient of the graph to calculate the acceleration. Finally, the acceleration time graph for constant acceleration is a straight line horizontal to the x-axis. The area under the graph can be used to calculate the velocity of the object at a certain time. Grade 10s, you'll find more information about graphs of motion at www.mindset.co.za/learn. Remember to try some of the questions in the task video too. Bye-bye.